In this video, I will be working out the Chapter 7, Day 2 notes. Here we are solving exponential equations and inequalities. In the previous day, Day 1, we looked at graphing exponential equations. And the biggest thing about graphing exponential equations is that these graphs had an asymptote. And the graph either had to be fully above or fully below that asymptote, where the graph doesn't actually ever cross or reach that line. Today we're going to take a step away from that and solve exponential equations, and the goal here, is to get these bases to be the same. So in the graph of the function, the thing that determined the rate of growth and kind of other parts to the graph was that base number b. And here you can see in problem number 1 that the base number for both of these is 2. When the bases are the same, all you have to do is set the exponents equal. So I'm just going to take 3x minus 1 and set it equal to 2x plus 6. And I'm just going to solve for x. I'll let you do that math. It just comes out to be 7. And you can even check your answer. If you plug in a 7 up here, 3 times 7 is 21, minus 1 is 20. 2 times 7 is 14. 14 plus 6 is also 20. So we've just made sure that that works out. And that works out to be a nice problem because the bases were already the same. So now number 2, what happens if you have to get the bases to be the same? What if it's not provided for you? So if you need to get the bases to be the same, you're going to try to change one or both bases to match the other. For example, look at this 9. Another way to rewrite 9 is as 3 squared. 3 squared is the same thing as 9, but now I'm going to copy that power, 2x minus 1. And if I keep the other side the same, you can now see that I have bases to be the same. So take this power of 2, distribute with the 2x minus 1, and then set that equal to 6x. And you now have a basic algebraic equation that you can solve. Just make sure to distribute. And then you'll see here that x should come out to be -1. And when you check this one, it doesn't work out to be as clear because if you plug -1 here and you plug -1 here, you'll get different powers. But you can type it into your calculator. So if I take 9 to the power 2 times -1 minus 1, I get this number, okay? Imagine that number in your mind, remember it. Let's do the other side. And there's that same number. So I've definitely checked my work here. All right, so let's keep going here. Sometimes you don't have to think too hard about getting bases to be the same like the previous problem. If I have 13 to some power equals 1, just ask yourself, what power on 13 will change it back to 1? What's the only power that takes a base and changes it back to 1? Well, the answer here is just 0, because anything to the 0 power is 1. So sometimes there might not be a whole lot of work to show for those special cases. And number 4 is a really important one because this question is, what power on 5 changes it to 0? And we know that the answer is not 0 because 5 to the 0 is actually just 1. So that actually doesn't help me. So what power on x, or what power for x, will change 5 back to 0? And this is where the graph comes into play. Your graph never actually touches 0 because there's an asymptote at 0. And so this means that there is no number that I can put on 5 as a power that will change it back to 0 because the graph doesn't actually ever get to that 0. And if it never gets to 0, then surely it doesn't get to any negative numbers. So for number 5, what power on 7 changes it to -49? Well, a lot of people think the answer there is -2. But if you remember from the graphs, 7 to the -2nd is actually 1 over 49. So that wouldn't be the answer either. And so if I can't reach 0, then I can't reach negative numbers as well. So this is no solution for the same reason as the last one, because of the asymptote. All right, let's get back to some ones that we can actually solve here. Number 6, 4 to what power equals 1 over 64? Well, let me try to get the bases to be the same. I know that 64 is the same thing as 4 to the third. 4 times 4 times 4 is 64. It's a perfect cube. However, my bases aren't the same yet because this 4 needs to be moved up to the numerator. So if I want to move that up to the numerator, that's where I introduce a negative exponent. This was a fraction, which is a big indication that your answer is going to involve a negative exponent. And you can see here that the bases are the same, so x equals -3, and now it's already solved. So there are times where you might have to introduce a negative exponent. For example, number 7, 1/2 would be better written as 2 to the -1st. Okay, so remember, 2 to the -1st is the same thing as 1/2. And we know that 64 is actually 2 to the 6. So here I changed both of the bases. This is the first time I've done this in the video. I've changed both bases at the same time because I wanted to get to a base of 2. So now I have this answer. Don't forget that negative in front of the 3x. So here x equals -2. You know, number 8, kind of a similar problem. 36 is 1 over 6 squared. But 1 over 6 squared is the same thing as 6 to the -2nd. And so then once you have that, you'll have bases to be the same. And you can find x from there. And here it comes out to be 0. So bases are the same. That's the goal. So I've got, I think, just 2 more on the back. All right, number 9. It's an inequality. It's an inequality, but I'm going to use the exact same technique. I'm going to try to get bases to be the same. And, you know, while 16 is 8 times 2, I can't think about it in terms of multiplication. I have to think about it in terms of powers. So 8 squared is actually 64. So I might need to change both of these. So 16 is 2 to the 4th. 8 is 2 to the 3rd. You'll notice there'll be some distribution for this problem, but also just copy whatever inequality you have. So this isn't going to be really any different of a problem besides the inequality sign. Forgot my sign here. So I will get x is less than 15 over 8. That's it. So let's do one more. Number 10. I have a base of 2, and then I have this 32. So I'm going to focus on the 32. 32 is 2 to the 5th, but I'm going to have to change that to a negative exponent. So I get x plus 2 is greater than -5. And so that leaves me with x is greater than -7. So these 2 problems on the back, very similar, even though they're inequalities. All you have to do is get bases to be the same, and then work with those exponents. Let me know if you have any questions. But that's it.